So let's start here. And so there's a gain of electrons and there's a loss of electrons. So as I told you, I would do some practice questions where you'll be asked to figure out the missing equations, right? So you've got this reaction happening, which is Na+1 gaining 1 electron in equilibrium with, it's in equilibrium with Na. And the E naught is minus, I think, 2.71 volts. And you've got another reaction, which is Cl2 plus 2 electrons. And it's in equilibrium and with 2Cl minus 1. And the E naught is 1.36 volts. And if you were asked who's going to gain electrons, the higher potential gains electrons, the lower potential loses electrons. So how did you construct the overall equation? You added up the reactants, but before that you made the number of electrons gained and lost equal. So I would multiply this equation by 2. Okay, so I've multiplied this equation by 2, and I'm going to make the number of electrons gained and lost equal. And we're going to add up the reactants and we're going to add up the products. So one way is I can rewrite the equation. Like this one is going in the backward direction. So I'm going to write it in the backward direction. It's going to be 2Na. That's my reactant. And the products are 2Na plus 1 plus 2 electrons. And what happened to the second one? Just a second. The second one was, this was Cl2. As you've got Cl2, and that Cl2 is it's gaining 2 electrons and it's turning into 2Cl minus 1T. So that's your second equation. And what would happen is you're going to add up the reactants and you're going to add up the products. You add up the reactants, you get 2Na, and you get Cl2. And you add up the products, you get 2Na plus 1, and you get 2Cl minus 1. Okay, is this clear so far?
Yes.
So this is what we have been doing. But now what I'm going to do is I'm going to remove one of the equations. I'm going to try, this is the oxidation equation. The first one is the oxidation equation. And the second one is going to be your reduction equation, right? So I'm going to remove the reduction equation, and we're going to try and do the reverse. So we have our overall equation, which is this one, and by looking at the overall equation and the oxidation equation, I'm going to find out or figure out the missing equation. So the missing equation is simple. Like this thing is going to add up with something, and it's going to give you this, right? So 2Na, what needs to be added? I mean, it's pretty obvious. There has to be a Cl2. Is this clear? And I'm going to find the missing thing over here. Like this thing would get added up with something to give you this. Like you've got 2Na plus 1, there's 2Cl minus 1 missing. So I'm going to write 2Cl minus 1. The electrons are always balanced. So the number of electrons that are lost are the same. So the same number of electrons would be gained on this side. TK, is this clear? I mean, this is a very simple equation and you'll be able to figure out the reduction equation. Is this clear to everyone?
Yes, sir. Still, where's the original equation? जहाँ पे you're considering it?
Which one?
I mean,
About this?
जी, हाँ जी.
This was the oxidation equation. They gave me the overall equation, which is this one.
अच्छा. Oh, अच्छा.
And we had to figure out one of the missing equations, right?
Mm-hmm.
Now, use the exact same concept which you just got over here, and we're going to try and construct. I mean, we tried doing this, TK, we just ran out of time. So we have our overall equation, which is this one. TK, so we have our overall equation. So this is my, this side is my reactants. That side is my products, right? So I have one of the half equations. I need the other equation. So what is the other equations? First thing, if you look at, so I'm just going to repeat this. So this is my half equation. Remember when I was making this equation, I did multiply it by 2, right? Why did I do that? Because I wanted the number of electrons gained and lost equal, right? So if you look at this equation, in your final equation, you have 6 O2s. So there should be 6 O2s over here. That means everything has to be multiplied by, you've got to multiply everything by 6. And if you do that, this would give you 12. This would become 6 O2s. This would become 24 H plus 1. And this would become 24 electrons. Okay, because this thing added with my second equation, which I have no idea what the second equation is, right? Right now, I don't have any idea, but this equation added with the second equation should give you this. Is that clear?
Yes.
So we'll now try and figure out what that second equation is. So we'll just once again. So what we'll just simply do is whatever is missing, like there's glucose. So where's the glucose coming from? That's probably coming from here, the second one. So glucose must be a part of this second equation. Where is CO2 coming from over here? I mean, this equation added up with the reactants in this equation, that gives you this. So this only has water. Where is CO2? 6 CO2s coming from? They must be coming from the second equation, right? The other half equation. What else is missing? Now over here, 24 electrons are being produced. So there must be 24 electrons being gained over here. But then that's why the electrons are getting cancelled out. But again, in the first half equation, there's 24 H plus 1, which are not showing up in the final equation, which means that 24 H plus 1 are getting produced. So they must be gained in the second one. That's why they're dissipating in the final equation. Is that clear?
Yes.
Yes.
And the final thing is that in my final equation, I've got 6 water molecules. If I add up these things, the reactant side, I have 12 water molecules, which means I need to get rid of 6 water molecules. So, because if I add them up, I'm going to get 12 water molecules, not 6. So that means there must be, you need to subtract 6 water molecules. Only then would the two equations add up to give me 6 H2Os, like 12 water molecules minus 6 H2Os over here. That would give me 6 H2Os over here. I mean, these two equations, they're going to get added, the reactants are going to be added up, and that would give you your overall equation. So I need to remove 6 water molecules. So there's going to be minus 6 H2Os. Now, if I add everything up, the electrons are going to get cancelled out. Like over here, there are 24 electrons being produced. So 24 electrons are being gained. 24 H plus 1 are getting produced. 24 H plus 1 are being gained over here. You had 6 CO2s, so I added 6 CO2s over here. I had 6 H2Os, but over here I had 12 H2Os, so I added minus 6 H2Os over here. So that
So why did you multiply 6 with this equation 1?
this one,
Yes.
I wanted the O2 to be balanced. Now, because final equation the O2 was 6, right?
जी,
So
यहाँ पे मैं
so there was only one O2 over here. Because remember when we add up the two equations, even when I did that, we would multiply the equations by a certain number so that the electrons gained and lost are equal. Is that clear?
जी.
So the individual half reactions are always multiplied by some number so that when you add them up, they gave us the equation. They just didn't tell us what that number is. I just figured it out myself that there are 6 O2s. So that means that this equation must have been multiplied by 6. So I found my second reaction, which is going to be, I'm just going to rewrite this. It's going to be 24H plus 1 plus this 6 CO2s plus this 24, they're gaining 24 electrons. And I'm going to take the water on the other side. So it's giving me 6 water molecules and C6H12O6. Is this clear?
Yes, sir.
Uh, I mean,
Ibra, is this clear?
Yes.
yes, yes.
Now let's move to the next one. I mean, there's only this question that has appeared that is like this. Let's move to the next one, which is draw a fully labeled diagram for the apparatus that should be used to measure the standard electrode potential of O2 in half equation one. What is the half equation one? I mean, it's this one. It's two H2Os. Uh, he's talking about the electrode, so I'm going to put a reversible sign. It's O2 plus, I think, how many H plus ones? Four H plus ones plus four electrons, right? So he's saying, how would you measure the E naught, the electrode potential of O2 in the half equation one over here? So this one is a gas, and this is aqueous science. Whenever you have a gas, the electrode is going to be a gas electrode. It's going to have a gas shower. So you're going to put, so you're going to make a gas shower over here. So let's say this is my gas shower. There's O2 gas that would be added here. And what else? It's going to be put in a solution. And the solution is going to contain H plus 1 ions. In aqueous state, water is always obviously there. Whenever you have a solution, there is water. And you're going to put a platinum electrode over there as well. So it would contain a platinum electrode. You have to fully label this. So this is the equilibrium that's established over here. And draw a fully labeled diagram of the apparatus that should be used to measure the standard electrode potential. Now I'm going to attach it with a voltmeter, and the voltmeter would be attached to what thing? I mean, what do you measure the voltages against?
Standard hydrogen potential.
So you're going to measure it against the standard hydrogen electrode, which is going to be H2 gas, and that's also a gas electrode. There's going to be platinum electrode, and there's going to be a beaker, and the beaker would have H plus 1 ions aqueous in it. So this is your zero potential. This is your reference electrode. And one thing is missing. I mean, you have to fully label it platinum. One thing is missing. What should I add?
Salt bridge.
The salt
Salt
bridge.
bridge.
Exactly. You have to add a salt bridge. You have to label that as well. Uh, so you can label this. This is a voltmeter. As anyways, they didn't, and it's a fully labeled diagram. And remember, he's using the term standard. So you have to mention the standard conditions as well. That the gas over here would be at 1 atmosphere pressure. I mean, this gas over here would also be at 1 atmosphere pressure. You can talk about H plus 1 aqueous having a concentration of 1 mole per decimeter cube. And I mean, this one is going to be the same. So it's a fully labeled diagram. We've labeled it. It's a 4-mark question. So remember, drawings are very important. You'll be asked to draw these things. Remember, there were 3 types of electrodes. One of them was where were the 3 types of electrodes? Metal aqueous ions, right at the beginning. I think this is no, not this. So now you had 3 types of electrodes. These are the 3 types of not these 3 types of electrodes, right? So you had a metal and aqueous ions. Whenever you have an electrode where you've got a metal, and the metal would be the electrode, and the ions would be in aqueous state. If you've got aqueous ions only, then you put a platinum electrode and put all the aqueous ions in the solution. And the third one is if you've got a gas, and the other things are aqueous ions. The gas would be in the gas jar, and the ions would be in the solution, and you'd put a platinum electrode in it. And all electrode potentials are measured against the standard hydrogen electrode. So those are the 3 types. The next one is for the cell drawn, use the data booklet to calculate the E naught cell and deduce which electrode is the positive. So we need to figure out the potential of this thing. Two water molecules, O2, 4H plus 1 plus 4 electrons. So where did the data booklet go? Sorry, just a second. So 1 second, data booklet. So it's 2H2O and O2 and 4H plus 1. So let's figure out if we can find that electrode. So it's probably I mean, this is 2H2O but no O2, so no idea where that is. It's this one. I mean, this is the electrode that he's talking about. H2O with O2 and 4H plus 1. So that's 1.23 volts. So this side is 1.23 volts. And this other side is your 0 volts. So what's the potential difference? Which is obviously like reduction potential minus.
1.23.
So it's 1.23. So that's 1.23. That's your E0 cell. And which one is your positive electrode? The positive one is the higher one. This is the lower one. Electrons are going to flow from towards the positive one, towards the higher potential. So 1.23, the left-hand electrode is the one. Left-hand electrode. That's the one. That's the positive one. Next one is you're given this reaction, and what is he asking? Use data from the data booklet to predict whether a reaction is feasible when aqueous solutions of acidified iodate ions and bromide ions are mixed. Explain your answer. So bromide, I remember the equation, it's Br2. I mean, bromide has only one equation in the data booklet, that's this one. So he's saying, is the reaction, this one is, I think, 0.5, 1.07. It's 1.07 volts. So this one is 1.07 volts. And we can double check. In B, it's, where did B go? As a bromine, it's 1.07 volts. As anyway, so which one is the higher potential? The first one is the higher potential, and the second one is the lower potential, right? So the first one is going to gain electrons, the next one is going to lose electrons. So the reaction is going to happen. The iodate 5 ions, which are these ones, IO3 minus 1, these are my reactants. And over here it's Br minus 1, which are my reactants. The two reactants are reacting together. Br minus 1 changes into Br2, IO3 minus 1 changes into I2. Is that clear? And
I mean, in what conditions would the reaction have not taken?
what conditions?
Yeah, I mean,
So I'll just tell you, just 1 second. After this, I'll explain this, okay? First thing is the E0 cell.
yeah,
The E0 cell has to be positive, right? That's when the reaction takes place. What is the E0 cell? It's the reduction potential
minus.
minus the oxidation potential. That should come out to be positive, right? Uh, so which one is the reduction potential? It's 1.19 volts. And the second one is the oxidation potential. That's 1.07. In other words, higher minus lower, that comes out to be 0.12, I think. It's coming
Yes.
out to. So that is positive. So E0 cell, that's what you're going to write. Explain your answer. You're going to tell them that the E0 cell is coming out to be 0.12. He's not asking for the equation, so I think it's pointless to actually construct the equation. He just wants whether it's feasible or not. It's just a 1 mark question. So no equations required, just whether it's feasible. You're just going to tell them that the E0 cell is 0.12, which is greater than 0. So that is when the reaction is going to be feasible. So let's say, Abrar, I'm going to try and answer your question. So let's think of it. This one is feasible, right? Let's think of a reaction that's not feasible. Let's say I want to figure out a reaction. I've got Na+1 reacting with Cl-1. The Na+1 changes back into Na, and the Cl-1 changes back into Cl2. Now, we know that this reaction is obviously not feasible. Like, we have NaCl salt, which is this one. NaCl just does not do this. It doesn't turn into chlorine, right? So we know that this reaction is not feasible. So how to prove that based on the E0 cell values? What are the two reactions that are happening? It's Na+1 in equilibrium with what are the two electrodes? It's one of them is this one. I'm just going to multiply it by 2 because I need to keep the electrons balanced. This is minus 2.71 volts. The other one is the chlorine electrode, which is this one. And it's going to be 2Cl-1. This is 1.36 volts. Now, if you focus on the equation that I've mentioned, what I want is, I want the equation to go, I want Na+1 to form Na, right? I want this reaction to go in the backward direction. At the same time, I want Cl-1 to turn into Cl2. I want this reaction to go in the backward direction, right? According to the reaction, I want to check the feasibility of this particular reaction. So I want Na+1 to change into Na. I want Cl-1 to change into Cl2. So if you calculate E0 cell, its reduction potential, which one is getting reduced? It's the first one, so that's minus 2.71, minus the oxidation potential, which is this one, so it's going to be minus 1.36. So the value comes out to be like really, really negative 3.97, I think. Minus. Ibrar, is this clear?
Yes, sir.
And based on common sense, it's obviously not going to happen because this one is the higher potential, right? Higher potential always gains electrons. It should be going in the forward direction. So what this minus value indicates is that the direction of the arrow that you've stated, the reaction is going to actually happen in exactly the opposite direction, not the way that you're suggesting. The lower potential loses electrons, so this arrow would go backwards, and the higher potential gains electrons, this arrow would go forward. So the reaction is not going to happen the way that you are suggesting. TK, is this clear?
Yes, sir.
TK, that's the reason why I don't prefer, when you calculate potential difference, I don't prefer higher potential minus lower potential, because they might ask you about a reaction that's not feasible. So it's better to use reduction potential minus oxidation potential. And if it comes out to be negative, that means the reaction is obviously not feasible. This one is highly not feasible. As the next one, you've got this one, the half equation. He's saying the aluminium is extracted from Al2O3 by electrolysis. Al2O3 is, so what's happening to Al2O3 is dissolved in cryolite. In this process, the half equation for the reaction at the anode is shown. So this is the half equation. This is the oxidation equation, I think. So you're given the oxidation equation. Use this half equation to write the equation for the electrolysis of aluminium oxide. So what is the reduction equation? I think this one, and he's saying use this half equation, write the ionic equation for the electrolysis. Does anyone remember what happens at the cathode? Like, you've got Al
Uh,
plus,
Cathode, reduction.
you've got Al plus 3. They're going to gain 3 electrons, and it's going to form Al, right?
Yeah.
So
Since
that's,
cathode is a positive terminal, right?
the cathode is the negative terminal. Electrolysis by cathode is the negative terminal.
Or
I said, also remember this. Anode is the place where oxidation happens. Don't, like in electrolysis, this is the positive terminal, and cathode is the place where reduction happens. I mean, this is by definition. The cathode and anode are not defined according to their charges. They're always defined according to. Just hold on 1 second. Just 1 second. I said, so remember, they're not defined according to their charges. They're defined according to what's happening there, right? So in electrolysis, where's a and in a cell, things are kind of opposite. Like if you've got a cell, which one of them is called a cathode, the other one is called an anode. Um, this is the place where oxidation is happening. I mean, chromium is losing electrons, right? So this is your oxidation is the place where anode is the place where oxidation happens. This one is the anode. Although in a cell they don't really use the terms anodes and cathodes. But if they were ever going to ask you about this, which I've never actually seen, but remember, if they ask you which one is the anode, which one is acting as the anode, this is the place where electrons are lost, and the other electrode is the one that's going to be called your cathode because that's the place where reduction happens. Is this clear?
Yes, sir.
So just remember, they don't really talk about anode and cathode when it comes to cells. But if ever they were going to ask you about this, the place where oxidation happens, that's the anode. As anyways, you have to write the overall equation. So you'll multiply this with 3, and this would become 6, and then you'll multiply this by 2, so that you've got the electrons balanced. And the overall equation would be 2Al 3 plus 2 3 O 2 minus, plus you have 3 C's, and the product are in the first one it's 3 CO plus 2 Al, I think. That's it. 3 COs and 2 L's. Okay, that's it. So that's your final overall equation. Next is we did do the Faraday constant, right?
Yes, sir.
So the next one is calculate the mass of aluminium that is formed. So you're given current, so you can use Q is equal to IT. And if you use Q is equal to IT, 1 second. So now if you use Q is equal to current into time, what would you get? It's 3 hours. Current is 3.5. So it's a large current. It's 3.5 times 10 power 5 amperes. And it's going to be multiplied by time, which is 3 hours, 3 into 60 minutes. And every minute is 60 seconds. Can anyone quickly do this and tell me what the answer is?
Three 3.78 times 10 to the power of 9.
So 3.78, sorry. Just a second. So it's 3.78 into 10 raised to the power 9, right? Coulombs. Now, how do you convert coulombs to number of electrons? 1 mole of electrons, it carries a charge of 96, 500 coulombs, right? So you've got 3.78 times 10 to the power 9 coulombs. So how many moles of electrons is this? So X would come out to be 3.78. What do we get?
3.92 times 10 to the power of 4.
How much? 3?
3.92 times 10 power 4.
So this is the moles of electrons that you're getting. Now he's asking for the mass of aluminium. We know that it takes 3 electrons to produce 1 aluminium. So we have the moles of electrons, which are these. So how much aluminium? Divide that by 3, you'll get the moles of aluminium. So what do you get?
He said, can't we multiply, use the formula that moles equal to mass over MR, and then we multiply this moles with MR and we get the mass of aluminum.
Nee, but the problem is these are not the moles of aluminium. Now these are the moles of the electrons that are flowing for 3 hours through the circuit.
Okay.
So first thing is you have to find the moles of aluminiums. Uske baad you have to do that. So so you divide by 3, what do you get? I mean, it's going to be 3.92 times 10 power 4 divided by 3. That's the moles of aluminium, and we know that moles is mass divided by mr. So if you take the AR on the other side, that's going to, you multiply it by 27. You'll get the mass.
So 3.53 into 10 raised to power 6, 5, sorry,
Into 10 is power?
5.
Okay, so it's 10 is power 5. So that's your mass. So just remember this thing. Q is equal to IT and Faraday constant. What does Faraday constant mean? It means that 1 mole of electrons, they carry a charge of 96,500 coulombs. So charge can be converted into moles of electrons. Moles of electrons can be converted into charge. Forget this equation. So let's try and do this one. Define the term standard electrode potential. So we wrote this definition. It's the potential difference. How do you measure the standard electrode potential? It's the potential difference of a standard electrode. Like we did 3 types of electrodes. So it's the potential difference of a standard electrode compared to what?
Hydrogen
Compared
electrode.
compared to the standard hydrogen electrode. That's it. So compared to the standard hydrogen electrode. So that's it. That's it for this one. Then he's saying draw a fully labeled diagram of the apparatus that should be used to measure the standard cell potential of Au3 plus Au and nitric acid NO. So it's a cell. You've got 2 electrodes. So I'm just going to quickly draw a rough diagram. The first one has a metal in it. So gold is going to be the metal, right? So let's just quickly do this. Gold is going to be the metal, and the Au3 plus ions are going to be present in the solution. So they would be part of the solution. The other one is a gas electrode. So it has NO gas in it. So there's going to be NO gas coming in, and there's going to be in the solution there's going to be nitric acid, which is going to be aqueous. Now for this you would need a platinum catalyst. So there's going to be label the platinum catalyst. Over here you don't need any electrode. The gold is the electrode. Use a voltmeter, connect the two together, add a salt bridge. Okay, so you're going to put a salt bridge in between, and that's it. Including all necessary chemicals. And remember, he's using the term standard, so label this properly. Label the platinum electrode. Label the salt bridge. Write 1 atmosphere with this. This is nitric acid, and it should be 1 mole per dm cube. Au3 plus ions, they should be 1 mole per dm
Then
cube.
nitric acid ko hum won't we write it as hydrogen ions and nitrate ions? Can we write it as a compound?
You can write it. It's nitric acid aqueous. that automatically indicates that it is dissociated. Achha, they didn't tell you about the reaction, but nitric acid and NO, I don't think this reaction is given in the data booklet. If we can go and have a look, nitric acid and NO. There is no, in N, there is no, I don't think anywhere there is NO gas. So, and there's no gold as well. Like there is no AU, A में होगा, ठीक है? If you go and find an A, there is no AU. So both of these electrodes, you don't know what the reaction is because they're not given in the data booklet. So the next part is, so they've given you the equations, right? And they've told you that, so they've given you the equations and they've told you that write an ionic equation to show the spontaneous reaction that occurs when electric current is drawn from the cell. So now you have a cell. The first one is the AU cell. The last one is your NO gas, nitric acid. I mean H plus 1, NO3 minus 1, NO gas, right? So the reaction is happening between the two, right? The first one, the middle one, I mean, like the electrodes that we draw, we didn't have any Cl minus 1 or we didn't have any AuCl4 minus 1. So we can ignore the middle one. Okay, that might be used somewhere else. So the first one is the higher potential. The second one is the lower potential. First one gains electrons. The second one loses electrons. The electrons are already balanced. So you just have to add up the reactants. It's going to be Au3 plus in the first one. And the second one, the reactant is NO plus 2 H2O. And the products are, in the first one, it's Au solid, right? And in the second one, it's NO3 minus 1 and 4H plus 1. Okay? So those are your, so that's it. That's your reaction. That's it. And so he's just told, he just wanted the reaction. Calculate the E0 cell for the reaction. So it's reduction potential minus oxidation potential. So it's 1.50 minus 0.96, and that gives you the E0 cell. This one is slightly more complicated. We don't have time for this. We'll do this one tomorrow then. TK, is this clear?
Yes, sir.
Yes, sir.
So we'll do this question tomorrow. Let's continue tomorrow. Okay, everyone.
All right, sir.
Take
Allah
care.
Hafiz.
Allah Hafiz.
Thank you.
Thank you.